Okay, so this video is about potassium, and it will serve as an introduction to your lectures. So what we're looking at here is the distribution of potassium in your body. So look at the top here. So total body potassium is about 3,500 millimoles. It's important to remember that all of potassium is dissolved in fluid as a solution. And the two compartments are the intracellular and extracellular fluid compartments. But potassium is distributed unequally, so 98% of it is intracellular, so living inside cells, and only 2% of it is extracellular. Where do we get it from? We get it from our diet. So on average, we probably take in about 100 millimoles per day. Foods that have the highest amount of potassium are fresh fruit, nuts, beans. So we take this in through our GI tract and we'll absorb most of it, about 95% of it. Maybe about the remaining 5% will be excreted in our stool. And this can increase in the setting of diarrhea. But we absorb most of it, and it's distributed intracellularly and extracellularly. Fortunately, we have the kidneys. And so the kidneys are really important for maintaining potassium balance because they have the option of fine-tuning how it handles potassium, whether it wants to reabsorb it. So it can take that potassium and dump it right back into the extracellular fluid, or we can excrete it in urine. And so pretending like we had 100 millimoles in the last day and 5 of them were excreted in the stool, the kidney would excrete the other 95 millimoles, with the goal being that everything in equals everything out. So if we add this up, we see that we've excreted 100 millimoles in a day. That way we stay in potassium balance. But consider a situation where we're depleted in potassium. The kidneys would reabsorb more of it to try and maintain the balance. Likewise, if you've eaten too many nuts one day, you had a diet high in potassium-containing foods, the kidneys would excrete more of it and enhance excretion in order to keep you in balance. One other important thing to consider is that these two compartments interact. Potassium can move from the intracellular to the extracellular environment. And then also, this is a tube over here with blood. Whenever we measure serum potassium, like in a BMP, we're only measuring the extracellular environment. And remember, most of it's intracellularly located. So just because the extracellular potassium that you measured is high or low doesn't necessarily mean that total body potassium is high or low. And the reason for that is because potassium shifting can occur from intracellular to extracellular or vice versa. And we will go over that more so in the next video. Okay, so now we've zoomed in and we're looking at a cell. More specifically, this is a cardiac myocyte. And we're looking at both the extracellular environment and the intracellular environment. And so what I want you to pay attention to is the difference in concentrations of both sodium and potassium in both of these fluids. So extracellular sodium, look, is about 150 millimoles. In reality, it's probably more between 130 and 140, but just to make the numbers easier, we're picking 150. Extracellular potassium is about 5, so think about what you see on a BMP. That's pretty close to normal. Intracellularly, I like to think that these are pretty much flipped from what you see extracellularly. Intracellular sodium, I'm listing here, is about 5 millimolar. In reality, it's probably more like 5 to 15. But intracellular potassium is 150 millimolar. So, easy way to remember this, they're just exact opposites of each other in terms of their concentrations. So why is this important and why does it occur? So this is important here because of something called membrane potentials. And I'll show you what I mean by that. But potassium is extraordinarily important in setting up the membrane potential for myocytes, especially cardiac myocytes. So as you can see here, the sodium-potassium ATPase works really hard to maintain these differences in concentrations. It will pump sodium from inside to outside of the cell in exchange for potassium, which it brings in from outside to inside the cell. So it wants to keep potassium high inside the cell, and it wants to keep sodium high outside of the cell. And look, it uses ATP, so it uses energy to do this. When this happens, what it sets up is a diffusion gradient. So lots of potassium inside, not as much outside. So potassium really wants to leak out and make it to the extracellular environment. Fortunately, there are these pores called potassium pores, and potassium will move through these pores. And one important thing to note is that at rest, so neurons and myocytes, when they're at rest, they are more leaky to potassium than any other substance. So potassium will leak out of these pores and go into the extracellular environment, and that is a diffusion gradient. However, notice over here that potassium is paired with these anions, and they don't want to be separated. So whenever potassium actually makes it through the pore, it's leaving behind some of these negative charges. And if you can imagine, as potassium leaves the cell, the inside cell environment is going to become more negative as these negative charges build up. So over time, as potassium leaves the cell, based on this diffusion gradient, the inside of the cell is going to become more negative. As the inside of the cell becomes more negative, it's going to start to counteract this movement of potassium because potassium's positive charge, it's a cation. And eventually it will completely balance out the movement of potassium outside the cell, and no more potassium will leave the cell. So what this is doing is making the inside of the cell negative with respect to the outside cell environment. So let's just put positive charges around here. Just to recap, diffusion will move from potassium from in to out, where this electrochemical gradient it's going to act on potassium to go from out to in. So it's counterbalancing the movement of potassium outside of the cell. What happens when the electrochemical gradient is equally balancing the diffusion gradient, the inside of the cell becomes negative, and what that sets up is something called the equilibration potential, or equilibrium potential. And that's what this equation over here can calculate. This is called the Nernst Equation, and as you can see, it's minus 2.3 RT over ZF log. So the concentration of something inside the cell divided by the concentration of the same ion outside the cell. So I've just added a simpler version of this equation, the Nernst equation. So assuming this is at room temperature and factoring in all these constants, it really just comes out to be minus 61 millivolts over Z. So this is the valence of the ion you're talking about. In all of our examples in this video, we're just talking about potassium, which is +1. So don't really have to worry about it. But if you're ever dealing with a negative ion, you have to make it negative. Or if the valence is more than 1, you have to account for that. So it's really minus 61 millivolts times the log of, so we're comparing the concentrations of everything inside the cell, so potassium in plus sodium in, all divided by potassium out, added to the concentration of sodium outside the cell. What these are right here are some modifications to account for the relative permeability of sodium across this cell compared to potassium. So remember, the potassium has the K pores. It's freely able to exit the cell and set up this gradient. Whereas sodium, when the cell's at rest, sodium channels are closed. There may be a little tiny bit of sodium that's able to sort of diffuse into the cells. But the relative permeability of sodium compared to potassium is about 1 to 100. So sodium contributes very, very little to the resting membrane potential, or this equilibrium potential. So potassium is the major player. But we're just including it here to be more complete. In reality, you could even add small contributions to calcium and whatnot, but we're just keeping it simple here. Okay, so here I've filled in some of the numbers. So minus 61 millivolts over 1 times the log of 150 plus 0.5. So small contribution over 5 plus 1.5. And I get minus 83 millivolts. So what this is saying is that for this cell at rest, with these concentrations inside and outside, assuming that the permeability of potassium is so much higher and contributes more than sodium, the cell will have a voltage of minus 83 millivolts compared to the outside. And this is what we recognize clinically, in that the RMP, so the resting membrane potential of a cardiac myocyte, so not when it's excited or depolarized, but when it's polarized, it's somewhere between 85 and 90 millivolts. And this is all due to potassium, because intracellular potassium is very high, extracellular potassium is very low, and it's permeable to potassium to let it leak out and set up this electrochemical gradient in the equilibrium potential. So here, feel free to work on these on your own, but notice how the resting membrane potential changes as the potassium outside the cell changes. So I really just plugged in extracellular potassium into that equation that we just did on the last screen, and calculated the resting membrane potential. So look, as the potassium outside the cell goes from 4 to 6 to 8 to 10, the resting membrane potential becomes less negative, right? So more positive, minus 88, all the way to minus 68. Over here, so remember heart cells, so they like to be around minus 90 or minus 80. This dotted line is probably somewhere around minus 55 or minus 60, represents the depolarization threshold. So normally cells are polarized at rest, and they need an action potential that comes along that depolarizes it, that makes the heart beat as all the cells depolarize at the same time. Correct? So what's happening as the potassium outside the cell increases, the resting membrane potential starts inching up. It becomes more positive, and it gets closer to the depolarization threshold. What this means is that it's just going to take less stimulation for the cell to depolarize. It may depolarize sooner than normal, and it may have a harder time repolarizing. So one thing that's important is that even after a cell depolarizes, in order for the sodium channels to become active again, you may remember this or not, it has to repolarize the membrane. Whenever the resting membrane potential is more positive and less negative, it's going to have a harder time repolarizing. We really like it to keep the resting membrane potential low. We like it to only fire an action potential whenever we're being properly stimulated, and we really like it to be able to repolarize easily. Whenever the resting membrane potential is more positive and is less negative, all those things are going to be more difficult. So it's almost like the cells are going to be more excitable, but once they're excited, it's going to be harder to repolarize them, and they're more likely to be refractory to further stimulation. This is why potassium is so important for the heart. So I did want to show you this real quick, the effect of potassium shifting. So as you'll learn in the next video, we do have medicines that can move potassium from outside the cell inside the cell. All right, and I hope you understood from the kind of the last thing we did before this one, which was that high potassium inside the cell is great. It's going to help lower the resting membrane potential. It'll make the inside of the cell more negative compared to the outside. And that will help repolarize the cell, and it'll make sure the cell doesn't depolarize automatically. So we want potassium to be high inside the cell. So let's do an example of potassium shifting and see what it does to the resting membrane potential. So pretend like you're seeing a patient with hyperkalemia with the outside potassium of 9. And so if we calculate this, we get about minus 70 millivolts. But imagine we had medicines and we shift potassium inside the cells, and look, we can move it down to about 6 or so. So extracellular potassium 6. The intracellular potassium goes up a little bit, but there's more intracellular fluid than extracellular fluid, so it doesn't go up, 1-to-1. So I saved that calculation for you, but when I calculate this out, I get minus 79 millivolts. So we didn't add or subtract potassium from the body. All we did was move it from outside the cells and pack more inside the cells. And look, that alone was able to increase the resting membrane potential for the cell, making it more negative, which is a safer place to be. The cell will be repolarized, it'll be ready to fire, and it's probably going to take like a real action potential, which is what you want to actually make the cell fire. This is why we do shifting of potassium to keep the heart safe, and we're going to go over that in the next video.